As I mentioned the previous hour, mechanical oscillations may be much more complicated than electrical oscillations. The differential equations themselves are more complicated. The wave equations is much more complicated. The wave equation of a thick plate is much more complicated than the Maxwell equations. And that's the reason why we get many different effects also in the mechanical world. So what we looked at before we looked at simple thickness oscillation. So simple thickness oscillation, if I look at it here, so thickness shear oscillation as this one shown here. Or when we look at the various modes, we only looked at thickness modes. Along the thickness we may have one half wave here, or 3 half waves, or 5 half waves, because odd mode overtones, even mode overtones are not piezoelectrically coupled to our electrodes. We only have piezoelectric coupling to odd modes overtones. But even this is a much simplified picture of the whole story. More detailed picture is given here. So here we have a quartz plate, a round quartz plate. Here you see here were probably the electrode attachments here. Observed as Bragg diffraction with X-rays, and the fundamental resonance, technical resonance is 3.2 megahertz. 3.2 megahertz is here, and this is its fundamental resonance. But besides this fundamental resonance, we have many more nodes, because thickness is much smaller than diameter of this quartz plate. We have many more modes in the transversal direction. All these transversal modes for the same basic thickness mode are happen at higher frequencies of the fundamental mode. Some of these modes may be very weak, like this. Why this mode is so weak? This mode is so weak because it has very little coupling on symmetrical electrodes. We only have coupling to this mode if the electrodes were not covering the whole, were arranged in a non-symmetrical fashion with respect to the circular cut plate here. So the excitation of these modes is very weak. While for higher order modes, we may have very much stronger excitations for higher order modes. And these modes are called anharmonics. These modes. They are related, yes, to the fundamental mode. They all happen at frequencies higher than the fundamental mode. They have much weaker coupling. You see here, they have much weaker coupling than the fundamental mode. The fundamental mode has very strong coupling here. Depending on the size and shape of the electrodes, we have more or less coupling. Some symmetrical modes have symmetrical modes have very weak coupling onto symmetrical electrodes. And here you can see all the solutions. In practical, these dots represent all solutions of the wave equation. What we are observing here, we are observing the diffraction at X-rays. If a certain part is oscillating, we have no diffraction from that part, or we have Bragg diffraction in other directions. So X-rays are here the convenient means to observe this kind of oscillation. So now let's see what this effect that describes here, this anharmonics, what do they actually do to our quartz plate? A quartz plate has a certain diameter, 2r. 2r prime is the diameter of the electrodes, and we only excite the fundamental transversal mode only under the electrodes, so this 2r here, 2r prime here. But besides the fundamental thickness mode, we get transversal mode very close to the fundamental mode. So for instance, if we take a typical quartz plate of 100 micrometers thickness and maybe 5 to 10 millimeters in diameter here, this high higher transversal mode, this anharmonics, will only happen between 100 kilohertz and 1 megahertz above the thickness resonance. This is the pure thickness resonance, and this is the complex thickness plus transversal mode resonance, is this thing here. And here we get many of these modes. So the transversal modes, we see this, them as a small ripple above the thickness resonance. So this is the thickness resonance, the series resonance, the parallel equivalent resonance. We get both peaks out of our equivalent circuit. But then we have spurious peaks happening, some say 200 to 300 kilohertz is usually, this is between 200 and 300 kilohertz above the fundamental frequency. Their strength, the strength of these peaks depends much on the shape of the electrodes, on the shape and size of the quartz plate. This may be as little as 6 dB below the fundamental thickness resonance, or they may be up to 40 dB down for a particularly well-designed crystal and well-designed electrodes. Like a crystal designed for crystal filters will achieve 40 dB of suppression of unwanted modes, at the cost that this only happens at one particular overtone frequency, at one particular thickness of the crystal. So this is very dependent on the crystal design. So each fundamental thickness resonance, so the fundamental, the third overtone, the fifth overtone, has these spurious transversal resonances that will cause us problems, especially in filters. Not that much in oscillators, because oscillators usually only oscillate on the highest mode, and these peaks still have an effect on the phase noise, but this effect on the phase noise is quite small, so it's not that bad. What we should also learn about this higher order transversal mode, they have a higher temperature independence, because each oscillation mode, the fundamental thickness mode or the higher order with all the transversal patterns, both thickness and transversal patterns, require a different angle of the quartz plate, different cutting angles of the quartz plate out of the base crystal. So if this one was temperature compensated by selecting the correct angles, then this here will have very high temperature dependence. In fact, we can even use these higher modes and their temperature dependence to measure the temperature of the crystal, and this is important for crystal ovens or temperature compensation of crystals in high performance oscillators. Or in other words, we could use different cutting angles for the fundamental mode to make out of it a very sensitive temperature sensor. So quartz crystals could also be used as temperature sensors. This was done in the past by Hewlett-Packard. Hewlett-Packard company built a temperature sensor with a quartz crystal plate cut at a specific angle. But we have to live with them. So now what is the angular dependence of this fundamental mode? So if we select phi 0 and theta 35 degrees and 20 minutes for the fifth overtone cut, but for the fundamental mode we need a somewhat different angle, delta theta, and this delta theta is shown here. You see this delta theta is shown as angular minutes, and you see what kind of temperature dependence of parts per million we obtain in our useful temperature range. You see that for room temperature, maybe here the green or the purple lines should be okay. But if our crystal is operating over a very broad temperature range, say from minus 20 degrees to plus 60 degrees, then the blue lines would probably be a better choice. Here, so a slightly different angle. So we can select this 80 cutting angle according to our application of our crystals. What is the expected temperature range we are going to use this quartz plate? Further, we can, in order to suppress this unwanted anharmonics, we can only work on the shape of the electrodes, or we can also shape of the electrodes you can see here. That they have different shapes, but only the overlapping area is important. Here they have different shapes, but we can also influence the higher unwanted anharmonics with the shape of the lapping of the quartz plate. So if we have a plano-parallel plate with two parallel sides, then we get some of these modes. But if we have a plano-convex lapping or biconvex lapping of the quartz plate, we get other modes. So it's possible to influence the anharmonics with the shape of the plate. What we are limited with the plano-parallel plate, we are limited to the thickness. In order for a crystal quartz plate not to break, it should be thicker than about 50 micrometers. If these plates here are about 150 micrometers thick, so not less than 50 micrometers, because with 50 micrometers this becomes too brittle, it may break easily. If we want to, so this limits the fundamental resonance below 33 megahertz approximately. This is 50 micrometer limited. Some companies are able to manufacture etched plate. So this inverted mesa etched plate may reach, in the active region, may reach a thickness of just 10 micrometers. It may be etched just from one side or from both sides. So we have a thicker outer ring for mechanical ruggedness of the quartz plate, and we have a very thin region in the center to obtain higher fundamental frequencies. So here we can reach 170 megahertz for the fundamental resonance, and of course higher resonances for the overtone, but only few companies are able to manufacture such quartz plate at this higher frequency. So if we need a higher fundamental frequency, then we can go to an etched quartz plate, or in other words, we can go also to other resonators. We will see this later on in this lecture. So what is the effect of the electrodes? If the electrodes are too thin, then they have quite a substantial metal resistance here, and the metal resistance degrades the Q, increases the series resistance of the equivalent series resistance here. This resistance is increased at very thin electrodes because it's the electrode resistance. But if we go on the other side to very thick plating, if we have very thick plating of the electrodes, these electrodes, actually metals, are not that good mechanical resonators as quartz, and the Q is degraded. The Q here is degraded by so the series resistance increases due to the mechanical losses inside the electrodes. So these electrodes, if they are very thick, they increase mechanical losses. Of course, putting electrodes thicker, also the fundamental mode shifts downwards with frequency. If we are loading the quartz crystals with metal electrodes, then its resonant frequency is shifting downwards. So this is just to explain that there is a particular thickness of the electrodes that it's ideal in this occasion here. Of course, any kind of dirt that accumulates on the quartz plate, so if dirt accumulates here on these plates, it also kills the Q of the resonator. And in fact, many resonators can be repaired if they are not hermetically sealed. They can be repaired by washing them in an organic solvent to remove any dirt from the quartz plate here, because dirt also kills the Q. How is housed such a crystal? So this was a crystal housing without the cover. The cover is soldered here, or in newer crystal it is welded. I used here somewhat older crystals so that I could remove the can without destroying the crystal. just by heating it. And the crystal holder, the housing of the crystal holder here, is actually a hermetically sealed container with a cover here that is soldered to the base. The base, of course, has feed-throughs for the electrical connection to the crystal. The crystal itself is held in position by springs. These springs, wire springs, are soldered both to the crystal and to feed-throughs for the electrical connections to the crystal. This is a two-point support. A two-point support is used in most cases for conventional quartz crystal resonators. But for high vibration environment like rockets or spacecraft, we use a three-point support, like a three-point support is shown here. This is a three-point support, but this three-point support was only used for the filter because we needed 3 electrodes here, while the three-point support is also used for high vibration environment like rocket or aircraft or spacecraft quartz crystals that operate in high vibration environment. This is the quartz plate, and this is the plating from one side, and from the other side silver or gold plating. Inside the housing, this is a hermetic housing, but inside the housing we just keep clean nitrogen at 1 bar at approximately the ambient pressure. So the shear waves here we also see the top of this package. The we also have represented the shear wave, the movement of the shear wave, and since we have shear waves inside, main waves are shear waves inside our plate, they do not couple to the to this nitrogen or air inside the crystal housing. So this nitrogen is actually not killing the Q of our resonator. If we had bulk if we had pressure waves here, pressure waves could propagate in air, while shear waves do not propagate in air. So this is the trick about crystal holders here. Modern crystal holders, not the FT243 from the Second World War. So this is how these crystals look like. Older crystals have the cover soldered, all the crystal housings, while new crystal housings have the cover welded. This is welded, this is welded, this is welded, while these are soldered, welded here. I also show on the same picture some ceramic resonators. Ceramic resonators do not achieve such a high Q, so they may have resin housings or even plastic housing. Because their Q is much lower than that of quartz crystals. Some quartz crystals may also have a plastic envelope around the metal can with soldered top here. Some good quartz crystals are round in shape. So good quartz crystals are round like this one here, because with the round shape it's easy to get the least amount of anharmonics. So these anharmonics here are the least with a round shape. But in expensive crystals, like for computer clocks, like this one here, this package is much smaller, but this has a rectangular crystal plate inside. Rectangular crystal plates are much worse in the terms of anharmonics. Rectangular crystal plates have much higher anharmonics than round crystal plates, so it's much more difficult to control the amount of anharmonics with such inexpensive crystals like this one here. But this inexpensive crystal was designed for a microprocessor clock, and so it was not required to be accurate at all. So this crystal was not a difficult item at all. While this crystal or this crystal filter here or this crystal was designed as a high quality crystal. So how do we make an oscillator out of a crystal? We can use a crystal as a tuned circuit, so we have its equivalent circuit here, right here. And most of the time we will use the crystal at its fundamental resonance. It does not have a highest Q, but it is the easiest to build an oscillator. An oscillator can be just a simple Colpitts oscillator where the crystal takes the role of the inductor plus some series capacitors for the DC operating point, and this is actually the simplest transistor oscillator, since the series resistance here is the lowest for the fundamental mode, not the highest Q, but the lowest series resistance at the fundamental mode. And also the transistor gain, the gain of the transistor is the highest at the fundamental mode. This will probably only oscillate at the fundamental mode. It's very difficult that this circuit will oscillate at overtones of the crystal if these two capacitors, C1 and C2, have sensible values. We can build the same as with a bipolar transistor. We can build that with a CMOS inverter. This is very typical circuits in microprocessors. We have just we need a bias resistor for the CMOS inverter to operate the CMOS inverter in its linear region as an LMN, as an inverting amplifier, and then we built our Colpitts oscillator with two capacitors and the series inductor represented by the crystal here. On many occasions we add a series resistor in series with the output of the CMOS inverter, because the output impedance of CMOS inverters is frequently way too low. Things are getting a little bit more complicated if we want to use our crystal at overtone resonances. So what do we have to do at overtone resonances? The most important thing is to kill lower order resonances, those that we don't want, because the crystal is usually always going to oscillate at its lower useful resonance, because the gain of the transistor is lower there and the series resistance of the crystal is also lower there. So the losses are the smallest at the lowest frequency the circuit is allowed to oscillate. If we replace this emitter resistor here with an inductor, if we replace the emitter resistor with an inductor here, then this parallel connection of a capacitor and inductor has an inductive impedance below its resonance and a capacitive impedance above its resonance. So for the oscillator to work, we need here a capacitive impedance of this circuit. So we have to keep the resonance frequencies of this circuit below the third overtone but above the fundamental, and in this way we force the oscillator to operate at the third overtone. If we went here above the third overtone, the crystal may oscillate then at the fifth overtone. But at the fifth overtone we already have the problem, because at the fifth overtone this admittance circle of the fifth overtone already goes very close to the real axis, so we may not get oscillation at the fifth overtone at all. That's the reason why for the fifth overtone we usually use more complex oscillator circuits. We have an oscillator circuit built with a filter. This filter is made by this tuned circuit here with a resistor and two capacitors. This is just a voltage divider built with two capacitors, and a crystal. A crystal connected to series. So the frequency is roughly defined by these tuned circuits, and then there is the fine tuning of the frequency with the crystal. In order to improve the performance of the crystal, we can compensate its parallel capacitance with a parallel inductor to the crystal. This, in theory, this may work, but in practice it is very difficult to make these things operate correctly. So you will only see this fifth overtone quartz crystal in very high performance oscillators when we need the very high Q of the crystal resonator at the fifth overtone. Otherwise you usually don't see this circuit. Even you don't see this circuit with microprocessors. Microprocessors only use this circuit here. This circuit with the additional inductor is used very rare with it's almost not used with integrated circuits with microprocessors. So the crystal, we should understand the behavior of the crystal. we should understand it by looking at its physical properties. So this is the crystal housing viewed from above. This is the quartz plate. And there may be dirt encapsulating inside this. At room temperature, there may be dirt. There may be vapors of dirt inside this package. And this typically happens with cheap crystals. So what happens with these cheap crystals when they are cooled down to below 0 temperatures? These vapors of dirt actually condensate on the surface of the crystal, and they actually dampen the shear waves inside the crystal, and the Q of the crystal, the loaded Q of the Q of the crystal decreases, and the oscillator stops working. So a typical problem of crystal oscillators, even in cheap electronics with microprocessors, is that microprocessors will not work below 0 temperatures because of bad crystals. And this effect is actually not repeatable because we actually do not know anything about the manufacturer, and his products are not repeatable. So different crystals may have different amounts of dirt vapors inside their package, and this effect may happen at different temperatures. So in order to turn on these oscillators, we have to heat quite much the crystal, so that this sticking dirt here evaporates in the housing of the crystal, and the crystal again raises its Q so that the crystal can start working. So there is a considerable, with crystals we see, with temperature, changing the temperature, we see a considerable hysteresis, temperature hysteresis, while cooling it down or turning it on, heating to turn it on. This turn off also does not happen when the oscillator is working, because if the oscillator is actually oscillating, this thing is moving. As long as this thing is moving, dirt particles will not stick to the surface. Dirt particles will only stick to the active surface of the crystal when the oscillator is off, when this thing is still. Then dirt condensates on the surface of the crystal. So this also depends on the operating of the crystal. So this turn off may not happen if we have the oscillator working, but if the oscillator is turned off at the same temperature, this will happen, because dirt will only stick to the surface when the crystal is not oscillating. So this is a very complex effect, and happens with most microprocessor equipment. So most microprocessor equipment will not start at below 0 temperatures. This is a problem in cold places, that the clock oscillators of your microprocessor don't start. If the clock oscillator doesn't start, your microprocessor will not work at low temperatures. But your microprocessor, if it's kept on all the time, it will continue oscillating, and as long as this is oscillating, dirt does not stick even at below 0 temperatures, and this starts running. But as soon as you turn it off, dirt sticks on the surface of the quartz and kills the oscillator, as long as this is not heated again up to much higher temperatures. This is a difficult effect to understand with crystals, but it's a big problem to build reliable microprocessor circuits using cheap Chinese crystals. This happens with cheap Chinese quartz crystals intended for clock applications. On some occasions, we may need to have the crystal oscillator frequency adjustable. Since the equivalent circuit, the values of these equivalent circuits are quite unfortunate. This capacitance here is 1000 times smaller than the capacitance of the electrode. Also, the tuning range doing anything outside the crystal is very restricted. So the tuning range is very restricted, especially if using an outside capacitor. If using an outside inductor, it's maybe so if you have an outside capacitor, here the tuning range is very small, while if you have an outside inductor, the tuning range is somewhat larger, but it may be useful at the fundamental frequency. It has less of an effect at third overtone, and it has almost no effect on the fifth overtone, because with the fifth overtone everything happens inside the crystal itself. Electrodes have very little effect here. We can also build this is a variable crystal oscillator. This is a voltage controlled crystal oscillator. With the varactor we can also tune our crystal. With the series inductor we can obtain more of a frequency change. This is also used in temperature compensating crystal oscillators, when we feed the VCXO with a voltage that tracks the temperature changes. So temperature changes change the frequency of the crystals. We correct that by changing the voltage applied to the varactor. So to build a TCXO. TCXOs nowadays are very good. They stay in the operating temperature range within 1 ppm, while conventional crystal oscillators like we have here, this maybe without any adjustment is 100 ppm, with some adjustment is 10 ppm, and with the TCXO it's 1 ppm frequency drift over the desired temperature range. Operating temperature range. With crystals, with quartz crystals, we can also build filters. We can build filters from discrete crystals. So with just one crystal, we can only build a simple bandpass filter, where in a bridge circuit we have to compensate the capacitance of the electrodes with an external capacitor. So this capacitor is used to compensate the capacitance of the electrodes here. We could not use an inductor like here, because the inductor would raise the response of the filter outside its desired frequency range. We can build a bridge bandpass filter with two crystals resonating at different frequencies. So these two crystals have a similar capacitance of the electrodes, but two different resonance frequencies, and this is a bridge bandpass filter for wider bands than this one here. And we can also build a double bridge bandpass filter when we have crystals for frequency 1 here and crystals for the second frequency down here. This is building crystal filters from discrete crystals. We can also make a ladder bandpass filter using crystals. This can be done with discrete crystals. It's more often done with bulk acoustic wave resonators, we shall see later. With crystals, we can also build on a single crystal plate. We can build a monolithic crystal that has one resonator here, another resonator here, that are mechanically coupling in between, and that are electrically coupling to the outside world, and of course a 3-point support to get the 3 electrodes outside of this filter. So monolithic crystal filters can also be built. The bandwidth of this filter goes from around 200 Hz for simple filters up to 50 kilohertz for complex double bridge or even quadruple bridge filters, crystal filters. So crystal bandpass filters can also be built. They are not that popular today, because today our digital communication requires much broader bandwidth than 50 kilohertz. This was used in the time of analog voice communications, where this filter much used, but nowadays they find little use. Built with quartz. So how do we have to specify a quartz crystal if we are ordering a crystal from a manufacturer? The manufacturer will take what is the equivalent inductivity of his resonances. In this inductivity we saw that it's almost the same regardless of the overtone. All overtones have the same inductivity, but what we have to specify to the manufacturer, we have to specify the oscillation mode. Since the oscillation mode defines the cutting angle, here we have the cutting angle of this is the angle of the cut of the AT cut depends on the oscillating mode. Different oscillating mode have different cutting angles for the best temperature, for the smallest temperature dependence of the resonance. So we have to define. We have the oscillation mode. If we are the manufacturer data will give the equivalent inductivity and the electrode capacitance here. And the customer requests the oscillation mode, of course the frequency. We can specify the series resonance frequency, this is uniquely spaced, or we can specify the parallel resonance frequencies at a certain parallel connected capacitor. This parallel resonance should be specified in oscillators like this. This kind of oscillator has a parallel capacitor. We should achieve its desired resonance with a parallel capacitor, so we have to specify here the parallel resonance. And of course the losses. What losses do we want? The lower the R, the more difficult, the more expensive the crystal, because we have low losses. The crystals without any parallel capacitor will have much further away its parallel resonance, but this is almost useless, because this is without any outside circuit, the crystal cannot be used really. So this is the way we specify a crystal when we order a special crystal to manufacture. Besides crystals, we have other piezoelectric materials. One such piezoelectric material is lead zirconia titanate. Lead zirconia titanate is very efficient piezoelectric ceramic. Of course, piezoelectric ceramic is an amorphous material, so it does not exhibit piezoelectric effects as it is right now, as it comes out of the furnace baking this ceramic. But before using this ceramic, we have to polarize this ceramic by applying a strong electric field, say voltages in the range of 50 to 100 kilovolts DC, to the ceramic plate to have this ceramic polarized. And then they exhibit quite a strong piezoelectric effect. We can build filters, we can build many resonators. For instance, on this picture here, we have 4 resonators on the same ceramic plate. We have two resonator mechanically coupled, these two also mechanically coupled, and we have a capacitor here on this ceramic to have electrical coupling between these two capacitors. So we have now a 4 resonator filter built on a single ceramic plate. This resonator can be built in the frequency range from about 3 MHz to 30 MHz. There are samples here on this picture of bandpass filter. This is bottom and this is above of the same filter, bottom and above of the same 4 resonator filter. This is for 6 MHz or 5 MHz. This one is for 6 MHz, the same thing. This one is for 10.7 MHz, this ceramic filter. Again, the same construction. This is for 6 MHz, 6 resonator filter in the same place. With ceramic filters, the Q is not particularly large, around 1000. The oscillation mode here is pressure wave. We do have some coupling to the surrounding air. We do not have a particularly high Q, around 1000 at 10 MHz. And velocities are in the 3 to 4 kilometers per second range. And if we don't want some mode, we dampen those modes with some resin. The resin, the ceramic resonator, is encapsulated in, actually dampens unwanted modes, also the unwanted anharmonics. So also ceramic has anharmonics, but here anharmonics can be dampened with the resin, the resonator is encapsulated in, and in order not to dampen the wanted resonance, we should also install cavities inside this resin. Okay, the cavities are filled with air, but the resin should not touch the resonator area. It should only touch the regions outside where this resin actually acts as an acoustic damper, as an acoustic absorber, to kill acoustic waves outside the region where we want them. So this is the solution how to build resonators using piezoceramics. These filters were very useful in the times of analog communications. So these filters were mainly used for the brown ones were used as bandpass filters for analog voice radio, while the blue ones here, the blue ones were actually 2 independent resonators. This contained 2 independent, not coupled because there was resin in between, not coupled, to be used as bandstop filters in certain television receivers. So in bandstops, in analog television receivers, the unwanted voice signal had to be removed from the video signal with a bandstop filter, also a ceramic bandstop filter. So in the case of analog communications, these filters were quite useful. They are not of that much use today. But still, we would need something else in our communications, not just quartz, because quartz is also limited. Quartz is limited, its fundamental resonance is quite limited by the plate thickness. We cannot do everything out of simple quartz plate, though they form the best possible resonators. But sometimes we would need something else. And that something else can be done with ceramic for relatively low frequencies, below 30 megahertz. But at high frequencies, say, where our mobile phones, where our smart mobile phones work, there we need antenna filters in the frequency range of a few gigahertz. So 1 gigahertz is a typical example, or 2 gigahertz for a UMTS phone. And here we can build filters as very thin films of piezoelectric materials. So as very thin films from aluminum nitride or zinc oxide. Zinc oxide was used in the older resonators. Aluminum nitride is used in the newer resonators. These resonators for 200 gigahertz operation, they are just a few micrometers thick. They are very thin, just a few micrometers thick. They can be done as films, so we etch the silicon from below, or here I will make a cavity on the carrier silicon wafer to have our resonators. These resonators may achieve a high Q, but these resonators cannot handle much power, because if these resonators are heated up by the radio frequency power, this power cannot be dissipated anywhere. So the idea is to use an acoustic Bragg mirror here. This Bragg mirror is consisting of sections having very high acoustic impedance like silica glass and very low acoustic impedance like tungsten. So putting here many layers of silica glass versus tungsten, silica glass, tungsten, silica glass, and having the period exactly here equal to half of the wavelength, we build here actually a Bragg reflector. A Bragg reflector to reflect all acoustic waves back into our piezoelectric resonator that's located here or here. It's the same picture, just a different drawing. This acoustic mirror it reflects the acoustic waves, but may dissipate the power. So with the finite Q here and the power of, say, around 1 watt of power here from the transmitter of our mobile phone, we can still handle that power dissipation of a few hundred milliwatts through the substrate here if we have this acoustic Bragg reflector here. So that's the idea behind. Of course, these thicknesses have to be very accurate, and there may be quite lots of these devices are rejected, so these devices can only be manufactured in very high volumes so that you can afford the rejection of many bad wafers to select out just good wafers on the desired frequencies. Also, the velocities are the acoustic velocities are higher, so we can go to higher frequencies also due to higher velocity acousticity, and the acoustic coupling is also quite high, so we can make broader resonators than we could do with quartz. So these are other materials are being used here for these film bulk acoustic wave resonators. With film bulk acoustic wave resonators, we can build filters, and these are mainly antenna filters for mobile phones. Since in mobile phones we need antenna duplexers, if in certain standards like UMTS the mobile phone is receiving and transmitting at the same time, we need duplexer filters, and these duplexer filters are made out of film bulk acoustic wave resonators. These filters are usually built as ladder filters, where you have series resonators and capacitor resonators. The pictures of these chips, these are chips actually less than a millimeter large chips. This can be integrated into chips so that they will fit inside the mobile phone. These are much smaller than electrical cavity filter. And you see here, this is a schematic of a ladder filter, of this ladder filter here. This is its schematic here. Or we have a schematic of this ladder filter here. Both these filters are infinite impulse response filters, as any filters. Also the crystal filters here were also infinite impulse response filters, as kind of filters. And you see the strange shape of the individual resonators. These are trapezoidal shape. These are even pentagonal shape. These resonators here. What is the idea? Or strange? This is not square. This is just a trapezoidal shape with all sides different. The problem here are the anharmonics. We also have anharmonics, as we have anharmonics in crystal plates. We have anharmonics, or here depicted here, the anharmonics. We also have anharmonics in film bulk acoustic wave filters. Here we have a filter for 933. We have a resonator for 932 megahertz fundamental frequency. You see that we have here many of these anharmonics. Many of these anharmonics happening with a simple square shape. But if the shape is not square, and if the shape is different from the different resonators, then each of these resonators will have its own harmonics at its own different frequencies. So the anharmonics of this resonator will differ from anharmonics of this resonator, will differ from anharmonics of these resonators, and so on. So we can build these resonators having just their fundamental thickness resonance at the same frequency, and have anharmonics and different frequencies, and so in this way we can improve the behavior of the whole frequency of the whole filter. We can get a better passband. This kind of filters are nowadays typically installed inside mobile phones on those frequencies where my mobile phones operate in duplex. When they are transmitting and receiving at the same time, the only solution are these film bulk acoustic wave filters. They can even be integrated in the same package as the transmitter output stage. On many occasions, these filters here have coaxial connections with one electrode grounded, but they can also be built as differential circuits. And this is also typical of today filters installed in mobile phones. Further, we can also build filters with traveling surface waves. Why with traveling surface waves? Because here we do not have the problem with the thickness of our substrate. Everything happens on top of this substrate, and we actually define the frequency operation of this filter with the spacing of the electrodes. In order to have a good, almost rectangular shape of the filter, we need at least one electrode shaped as sin x over x. You see inside here the sin x over x. So the sin x over x shape in the time domain, because we have here time domain, equals to a rectangular response in the frequency domain. So we can shape actually the response of this filter. This is a finite impulse response filter. We can shape it by the shape of the electrodes. We need acoustic absorber at the beginning, at the end of the filter, not to absorb unwanted acoustic waves propagating in unwanted directions. As a substrate, we can use quartz here. Quartz has the highest stability but the lowest piezoelectric coefficients. We can use lithium niobate. This is very popular in mobile phones. We can use lithium tantalate that has an even stronger coupling. And we can use even exotic crystals like langazite. Langazite was actually invented by Soviet-era scientists for a space war laser, but the laser didn't work for some reason. But it's a very good material for building filters. So they didn't do anything for Star Wars, but those scientists invented a very good material for making filters. Velocities are between 2 and 5 kilometers per second. surface acoustic wave filters. And these filters are finite impulse response, so they're maybe easier to work with. The only problem is the loss of signal here and the loss of signal here. So surface acoustic wave filters usually have a high insertion loss. On this picture we have a photograph of a very old surface acoustic wave filter used at 36 MHz for the intermediate frequency of analog television receivers. You see here the electrodes on one side are simply all of the same shape, so this is the two pair of electrodes here, fed in symmetrical fashion, in differential fashion, while on the other side we have sine x over x inside of the electrode. You see the sine x over x shape of the electrodes here, and there are many electrodes in between here, and this sine x over x shape actually will give a very nice rectangular shape filter as required in an analog television receiver. And at the beginning and at the end of the filter we have this green resin here, and this green resin is actually an acoustic absorber to remove unwanted waves. There are other ways to remove these unwanted waves, but with cheap filters for cheap television receivers, so with more complex electrodes we could remove the acoustic waves otherwise, say building a 4-phase feeding electrode, so to have the acoustic wave just in one direction. But for cheap filters with just one pair of electrodes on each side, we use resin here, and the insertion loss of this filter is very high. It's 3 dB for this absorber, 3 dB for this absorber. Further, the loss in the lithium niobate, it's usually above 10 dB, usually 15 dB, even up to 20 dB insertion loss of this filter. But this was a cheap solution for analog television receivers. It is used, the same technology is used nowadays for mobile phones, but since mobile phones operate at 10 times to 100 times these frequencies, these electrodes have to be spaced at 10 times to 100 times smaller spacing, so you can no longer take a picture of those electrodes with an optical microscope. You would need an electron microscope to actually see those very small electrodes of a GSM filter. Well, this is a relatively low frequency surface acoustic wave filter, and here you can see with the simple microscope you can still see the electrodes here. You cannot see that with surface acoustic wave filters for higher frequencies. One final solution besides complete filters, as finite impulse response filters with a traveling surface acoustic wave, we can also build resonators with a standing surface wave, where we have a pair of electrodes here to excite the oscillation inside the mechanical oscillation inside the piezoelectric substrate, and we have Bragg mirrors on both sides, mechanical mirrors made from the same electrode material as the two electrodes are made. If the spacing here is lambda half, where this big lambda is acoustic wavelength inside the piezoelectric surface, we reflect the wave here and reflect the wave here, so we can obtain a very high Q resonator also on a piezoelectric substrate that may have a similar thickness. So this can also be made, and with many of these resonators are used as single resonators for some very cheap transmitters like remote control transmitters, but they can also be used inside filters like this, inside ladder filters like this. So these resonators may be bulk acoustic wave resonators like here, but could also, each of these resonators could also be a surface acoustic wave resonators. If I'm talking about today's technology, both technologies do compete. Surface acoustic wave resonators, so standing wave, also competes with traveling wave and competes with bulk acoustic wave resonator, film bulk acoustic wave resonator. So these are competing technology. It seems that bulk acoustic waves resonators, they are cheaper, or they can be made better above 2 GHz, and below 2 GHz that surface acoustic wave filters prevail below 1 GHz. So, but this is a technological issue of what is being built inside our mobile phones. These filters do not have a particularly high Q. The Q unload is around 2000, so maybe we can use a loaded Q of 200, and still we have quite an amount of transmitter power dissipated in this filter structure. So we still have high losses in this filter. So talking about mobile phone frequencies about 2 gigahertz, these filters may have a bandwidth of 20 or 50 megahertz. So a few tens of megahertz bandwidth can be done with FBAR filters. Not less than that, because losses go too high with the limited Q we have available. So for very low noise resonators, for very low noise oscillators that need very high Q resonators, still our quartz crystal is the best choice we can think of. Our quartz crystal is actually the best we can make, and there is actually no replacement, no cheap replacement for it. There are very expensive replacement, very bulky, very large, but very small resonators that we can build inside the mobile phone. They are only quartz crystal, and quartz crystal for this reason is perhaps the most important application of silicon in electronics, more important than integrated circuits and more important than optical fiber, because we have actually no replacement for this component here. We could replace this one, we could replace this one with vacuum tubes, but there is no replacement for the mechanical resonators. So to see our future lectures, now we have to see what to do, what we have to think about modulations. If we have such good oscillators, or whatever oscillator we have, what kind of modulation we can use to transmit our information, regardless if that is analog information or digital information. We have to see that in our next lecture next week. Talking about quartz crystal, there is also a very nice movie on manufacturing such historic quartz resonators during the Second World War in the United States. It's available on YouTube. It's called Crystals Go to War, and it deals with many of the aspects of quartz crystal manufacture, including the X-ray machines, including the plate manufacturing, oscillations, and so on. So that's a very interesting movie on YouTube. I recommend it. The movie lasts around half an hour. I will give the link for this movie together with the lectures.